All right. Hi, everyone. Thank you so much for being here. My name is Olivia Gallucci, and I'm a security engineer at SECUINFRA, which is a security consulting, MDR, and research firm in Germany. And today, I'm going to walk you through the foundations of macOS internals and how to start exploring them using Apple's open source code. So what are macOS internals? macOS internals are the underlying components that make the system work. So like the XNU kernel, process and memory management, system libraries, syscalls, device drivers, basically everything that runs under the graphical user interface. It's the difference between what you click and what's actually happening when you click something. macOS internals matter in so many contexts, such as security research, performance tuning, or debugging weird system behavior. It lets you analyze vulnerabilities, understand potential undocumented features, or even patch behaviors. And there's a bonus for iOS researchers, which is that iOS shares its core with macOS. Now, I want to address the elephant in the room, which is Apple's secrecy. And its secrecy is problematic for a number of reasons, but it's a myth that Apple's 100% closed source. Okay. A large chunk of macOS and iOS is actually open source. Apple publishes the XNU kernel, system libraries like libc and libdispatch, daemons like launchd, and various other things. Anyone can go online and read the code that runs on a Mac or iPhone. Of course, Apple doesn't release everything. Some frameworks like Core Foundations and UIKit are closed. But what is public is incredibly useful if you know how to find it and work around the gaps. Now, let's explore the intersection between computer architecture and Apple's open source software. So to understand, Apple's operating system sphere and its open source, we got to start with Darwin. Darwin is Apple's open source Unix-like operating system. It's the foundation of both macOS and iOS. And at the heart of Darwin is the XNU kernel, short for X is not Unix. It's a hybrid of the Mac microkernel and BSD. Mac handles task scheduling, memory, and interprocess communication, or IPC. BSD adds the POSIX APIs, networking, and file systems. And IOKit, written in C++, manages the hardware drivers. And if you're interested in all of that, I actually gave a presentation on this last week. But yeah, so there's some other things in this mix too, but we're not going to really get into those today. The main point is that when Apple builds macOS or iOS, they're layering proprietary features like the GUI and frameworks on top of Darwin and XNU. So yes, macOS and iOS literally run on the same base OS. And here's just a cool diagram of how Ubuntu and macOS compare. I figured this might be helpful to include for some folks. It serves no other point in that it is interesting to look at and kind of helpful. So yeah. All right, let's explore this shared foundation. So here's a table comparing some system daemons and services. There's actually tons of these. I just only had space for like 4. You'll notice, that launchd, mDNS responder, the preferences daemon, PowerD, and others run on both platforms. Sometimes they're even identical. Because of this, vulnerabilities found in macOS daemons can also exist in iOS too. And as you can guess, this is an advantage for security researchers. You can debug and reverse the macOS binaries, which are easier to work with in my opinion, and then apply that knowledge directly to iOS. Another important note is that in general, iOS is considered to have more restrictions because it has stricter sandboxing, entitlements, and application isolation. But underneath those constraints, the code is often the same. So what is actually available? Apple publishes a range of open source components like the XNU kernel, core libraries like libsystem, libc, libdispatch, and daemons like launchd. They are all downloadable, inspectable, and sometimes even buildable. But they don't publish everything. Missing or partially available components include Core Foundation, CF Network, launchd in recent releases, iOS-specific drivers, the full dynamic linker, and their core crypto library, which is called core crypto, which comes with legal restrictions like a 90-day then delete policy. A quick note about this deletion policy. Apple announced in 2015 that it would disclose the source code for 3 crypto libraries. Crypto, also, just crypto is cryptography in this case. There's Core Crypto, Common Crypto, and the Security Framework. However, Core Crypto's license is an internal use agreement, not an open source license. So by downloading Core Crypto, you must be an authorized Apple developer and explicitly agree to Apple's Core Crypto internal use license. And under that license, Apple grants you a 90-day limited, non-exclusive, non-sub-licensable license solely to copy, compile, and run Core Crypto within your organization and within your own devices, for only the purposes of verifying the code security and correct functioning type of stuff. You must include the license in all copies, and you may only use this license for that verification purpose. And again, this license ends after 90 days, and upon termination, you agree to cease all use of this software and then destroy all the copies. In other words, these types of things, like this 90-day deletion policy, is one of the other factors that kind of hinders researchers here. So on top of that, Apple's source drops are often incomplete or outdated. You'll see headers referencing files that don't exist or tarballs with no build instructions. So while Apple's open source is a gold mine, I think it's important to approach it knowing you're going to hit some walls. The big idea here is that macOS and iOS share the same core. Apple open sources, more than people think, but not everything, and navigating that code is essential for internals research. All right, now we're going to talk about how to actually find and use this open source code. So again, Apple's open source a surprising amount of code, but the company, from an outsider's perspective, has also kind of redacted / kind of hid past releases of said code and has moved a lot of this code around online. Thus, depending on how you're going about accessing this code, it can be really difficult. For example, a tutorial written from 4 years ago might include links to exclusively 404s if that tutorial links to downloads or source dumps of Apple's before 2024. So then where do you find this code, and what does 2024 have to do with it? Historically, Apple published source code as gzipped tarballs on its open source website. These archives were organized by macOS version, so things like XNU 8792.4. tar.gz or whatnot. And that worked until it didn't. In March of 2024, Apple began retiring these direct downloads. Now the primary home is its GitHub organization called Apple OSS Distributions. Each component now has its own repository tagged by version. So instead of downloading from Apple's website, you're grabbing release zips or browsing repositories on GitHub. So now, how do I navigate GitHub? Well, each repository has that basic format starting with a name like XNU, libdispatch, or libc. And then a set of tags like XNU 8792.4.9, which map to a specific OS version. And sometimes there will even be a release field, if you're lucky, that tells you which macOS or iOS version it matches. But the catch here is that Apple doesn't just explain these mappings. And this is extremely important because you can't often explore these things properly if you're not using the exact Xcode version used to develop that specific component or version. For example, XNU version 8792.4.9 corresponds to 41.9 corresponds to macOS 13.4, but Apple doesn't tell you that. You have to infer it by checking their release pages or using community lists. I personally use Wikipedia's version history. Unfortunately, there's many challenges, with Apple's open source releases, and I'm going to cover the three main ones. First is delays. Code usually appears weeks or months, maybe even years after the OS ships. There's no warning, no schedule, just a coming soon notice. Sometimes even for 6+ months after the OS ships, it will still have that coming soon notice. Next is incompleteness. Some tarballs are missing files, headers reference code that's just not there, and then entire components like Core Foundation or newer Launch D builds are just MIA. And then lastly is tag confusion. Tags like XNU 8786, blah, 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 mean nothing unless you know how to decode them. And that's why learning how to map Git tags, learning general project structures, and also just knowing how to use Git and GitHub in general is really important in these situations. Now, I want to explore a few more tips that I use. First, I check the release field in the GitHub repository metadata, again, if it's available. If it ever says something very explicit like macOS 13.4, that's gold, use that. I also use Apple's distribution manifest to cross-reference components per release. Distribution manifests are XML files used by Apple's installer to define and orchestrate the content, scripts, and conditions of macOS package installations. This makes them valuable to uncover installation logic, component versions, and hidden behaviors. Also, Apple's distribution manifests are embedded inside Apple's installer packages. For example, you'll download like a .app or a standalone package or like PKG. You'll right click and you'll put like show package contents, and then you'll find a file named distribution, which is an XML manifest at that top level. And lastly, I look for clues in the binaries themselves. So like version strings or source file names with the strings or what programs to figure out where a binary came from. And so what I've learned is that finding the source code is doable, it just could be really messy. And again, Apple doesn't make this easy, but with GitHub, a few sleuthing tricks and some trial and error, you can usually track down the source code for many major system components, with the caveat being that it might be from a much older version from a very long time ago. So yeah, now I'll actually show you how to use the source code, especially when it's incomplete, to do reversing and security research. Specifically, we're going to look at how to use Apple's open source code to examine system binaries. So even though the code is often incomplete, it can still guide your research. The key is to treat it like a map. You might not have the full territory, but the landmarks are real. And what I do, and what many other security researchers do, is use Apple's open source code as a reference while working with the binaries. They'll take a binary like launched, syslog-d, a kernel extension, or whatever you want, and use the available source code to do various things. For example, I might try to match known functions. This helps identify familiar code in binaries, making it easier to understand behavior and verify functionality against Apple's open source implementations. I might also try to annotate call patterns, which reveal how functions interact and in what sequence, allowing me to infer program logic and detect deviations from expected or unexpected behavior. Lastly, I might try to reverse any unknown logic. Although this is difficult, attempts at this enables me to uncover the purpose and or vulnerabilities of software that lacks source code, using either structure or context to reconstruct what it does. Essentially, when symbol names are stripped, you can use structure, string contents, or known syscall usage to map back to the open source code. And here are I'm going to go into 4 tools for this. But if you've already been in the reversing space, these tools probably aren't new to you. Of course, there's strings, which dumps human readable strings. Sometimes these include debug messages, file paths, or format strings. Then there is what, which extracts version and project information from binaries. And there is nm, which lists symbol names, especially in unstripped binaries or frameworks. So an unstripped binary contains symbols and debug information like function names and variable names, whereas a stripped binary has had that information removed to either reduce size or hinder reversing. Apple publishes source code for many components via its open source sites, but it doesn't distribute the unstripped binaries. Instead, the downloadable macOS packages only contain the stripped binaries. So quick detour, what does that mean? An unstripped binary contains symbols and debug information like function names and variable names, whereas the stripped binary has that information removed to reduce size or hinder reversing, right? And as I said previously, Apple's macOS installers and update packages do not include unstripped symbol-rich binaries. In fact, Apple's default build settings strip out debug symbols. You can see Xcode's retain raw binaries defaulting to no, and so if you end up wanting to do this stuff at home, you're going to want to look at that. So in practice, all shipped system binaries from kernel to /bin/user /user/bin executables are all stripped of the local symbols. Okay, yeah. And again, there's no public repository of just unstripped versions. Oh, and if you do want some sort of unstripped version, you can get them via the developer-only downloads. For example, the kernel debug kit on the Apple developer site or via the special symbols packages. Thus, if you need symbol information for a macOS system binary, you must rely on these Apple developer resources such as the KDK, DSIM files, and or rely on that open source code, as I stated. Oh, and I just realized people might not know what this is, but the KDK DSIM files are like debugging symbol bundles included in Apple's kernel debug kit that contain DORF metadata for the macOS kernel and its extensions, enabling symbol resolution during kernel debugging. And then the DORF metadata is just a standardized debugging information format that maps the compiled machine code back to the source level details like variables, types, and line numbers even. All right, yeah. Oopsie. Okay, yeah. So in short, none of Apple's end user macOS downloads include debug symbols. And now we're gonna just get back to the tools. So there's one more tool I wanted to cover, which is class dump, which extracts Objective-C class and method definitions. It's great for finding interface information, and through using all the tools we just discussed, I can usually figure out which open source package a binary came from or what API it's using, even if I don't have the source code for that exact version. All right, and so before we get a bit deeper, I want to cover a couple more like basics before really getting into internals research, because it's kind of information you will need to have once you start looking into these things. The first is Objective-C and Swift. These are the primary languages used to build macOS and iOS applications. Objective-C is the older legacy language still found in many system frameworks and older apps. Swift is the modern, safer, and preferred language for new development across both platforms. And then understanding both of these languages is helpful for reversing binaries, because system binaries, apps, and APIs are built in these languages. So you kind of want to know what you're looking at, right? And then the things that you're going to want to learn specifically is like their syntax, their memory models, and their runtime behaviors, because these can reveal how code interacts with the device frameworks and the underlying OS internals. Another thing to know about is Xcode. Xcode is Apple's official integrated development environment. It is a large download, and it's used just for creating software on Apple's operating systems. It provides the tools to tools, compilers, runtime support needed to either write, build, or debug and run Objective-C and Swift applications. And it also exposes things like frameworks, debugging tools, and system headers, which are OS-provided files that declare system APIs, types, and macros that help analyze how software is structured and functions. Yeah, anything else to cover here? Oh, yeah. Knowing Xcode is really helpful with reversing because it provides integrated tools for inspecting, debugging, and rebuilding Mac-O binaries and their symbols within a familiar development environment. A great person to watch here is a guy named Bryce Bostwick. He has tons of videos where he debugs and reverses iOS apps. He has a really great setup too, which lets you see exactly how he uses the IDE and other tools throughout his workflow. There's also disassemblers and debuggers. A debugger lets you run and control a program to inspect its execution, while a disassembler statically translates compiled machine code into assembly instructions for analysis. In general, debuggers are valuable for observing and manipulating a macOS component's live execution, like setting breakpoints, for example, or inspecting memory and tracing API calls. While disassemblers let you statically examine the binary's machine code and reconstruct its logic to identify security-relevant routines and vulnerabilities. So there's a lot of tools in this sphere. I'm just going to give a brief one-sentence overview of each. And so some of your employers might have corporate versions of these tools, so you might want to see if you have some of these available already. The first is Hopper. Hopper is a macOS and Linux tool that disassembles and decompiles binaries, letting you, analyze the decompiled code, right? Ghidra is a free and open source software suite from the NSA that offers, disassembly, decompilation, and scripting for a wide range of architectures. Binary Ninja is a commercial platform by Vector35, and it has a built-in decompiler, interactive analysis features, and a Python API for automating inspections. Last at least in like the application domain, is the IDA interactive disassembler, which is considered like the industry standard. It's a proprietary disassembler and debugger by Hexrays, and it's known for its interactive analysis and decompiler plugin. Now we're going to move on to strictly the debugger space. There is LLDB, which is the default debugger on macOS. It's part of the LLVM project and is used for stepping through code, setting breakpoints, inspecting memory. For reference, LLVM is the modular compiler infrastructure and toolchain framework. It includes like CLang and LLDB. And this is all foundational for building, analyzing, and debugging macOS binaries for understanding compiler-generated code and runtime behavior. There's also, GDB, which is the GNU debugger available for many platforms. And I will say, though, this is a little bit less common when it comes to macOS stuff, and I believe it's due to like a code signing issue. Don't quote me on that, but that's what I'm pretty sure is why it's not as common. And then there's also Frito, which is a dynamic instrumentation toolkit that lets you hook and instrument functions at runtime, effectively acting as a debugger for live processes. So Frito is kind of like a high-tech stethoscope and scalpel, letting you kind of listen in onto a program's heartbeat and even perform surgery on its functions while it's still awake and running. In reality, dynamic instrumentation is the process of modifying a program's behavior or collecting data while it's running, again, without changing the source code or restarting it. In the analogy, dynamic instrumentation would be the act of like placing the stethoscope somewhere or using the scalpel while the patient, aka program, is fully conscious and functioning, which would be kind of scary, right? This allows you to monitor or tweak what's happening without, pausing or cutting the patient open beforehand, without stopping or modifying the source code. Another example of this is hooking. In reality, hooking is a technique used to intercept function calls or messages in a program to observe, modify, or redirect their behavior. But in the analogy, hooking is like attaching a sensor or rerouting a nerve signal mid-surgery. You intercept a specific signal, like a heartbeat or a reflex, to observe it and change its response, or send it somewhere else, all while like the body, aka the program, continues to function. Lastly, there is instrumenting functions at runtime. This component injects code into functions of a live application to monitor or alter their execution during a program's operation. In this analogy, this component is like inserting a tiny medical tool or monitor directly into a specific organ or system while the patient is awake. This way you can watch how they behave in real time, collect data, or even tweak how they work without ever needing to stop the body's natural processes. And overall, this tool and process is useful for macOS internals research because it allows you to observe, analyze, and modify the behavior of system components and processes in real time without ever needing to, the source code or restart the whole system. Also, if you want to, set up Frito on macOS, there's a really great 3-minute tutorial by a guy named Tom that just walks through this process. It's a really great tutorial. In reality, it will probably take you much longer than 3 minutes to set it up if your MacBook isn't already configured, but he explains everything in a really straightforward way, and he just does such an excellent job. So yeah. So in terms of independent tools, the last one we're going to cover is Radare, which is a built-in debugger that supports scriptable debugging on multiple architectures. One other note is that there is an IDA Pro debugger that allows you to run and analyze programs interactively while using its disassembler, as well as a Binary Ninja plugin-based debugger that supports breakpoint management and memory inspection. I do not have a strong favorite, but I have the most experience with Ghidra, primarily because it's free and accessible. I also appreciate that Binary Ninja offers a student discount for those things, and that goes a long way when you're trying to learn on a budget. I just graduated from my undergrad 3 weeks ago, and I will say that finances have definitely played a role in which tools I choose to explore. And again, reversing tools can be quite expensive, and as someone fresh out of school and managing these life changes, that's why I'm gonna stick with Ghidra, right? But I will say, if you're interested in the way that I do plan to explore these tools, I'm starting with Binary Ninja, and because they offer the student discount, and I gotta support those companies, right? And then hopefully I'll work my way to the others. But yeah. Oh, one more note is that there's a lot of debate about which tool is the best, and although some of that debate is valid, I think it's kind of similar to choosing a programming language. When you're starting out, that choice feels huge, but once you pick one and get comfortable, switching languages or tools in this case becomes much easier. And after gaining some experience, you kind of look back and realize that agonizing over which one you were going to choose to start learning, to start experimenting with was just kind of silly. And the reason why I kind of know this is that I've experienced with like all of these tools, and learning how to use them like took me like 30 minutes, except for the initial learning how to use Ghidra, because it was just like, whoa, there's lots of stuff I don't understand, right? So, all right, now we can continue with this process, right? We've covered all the tools, all of those things are like all you would ever need to know to start this process. You don't have to use all of them, but I just want to get back to kind of like this research flow, right? We can advance to the point of where I would start to try to get a bit deeper if I thought I found something, right? And at this point, I would use a process called binary diffing, which is the process of comparing two compiled binaries, typically before and after a patch, to identify changes, which helps pinpoint patches or vulnerabilities even without source code. Tools like bindiff and diaphora let me compare two binaries, say again, before and after a patch, and maybe spot the changed functions. To give a theoretical example, let's say Apple silently fixes a vulnerability in System D. I could try to diff the old and new binaries and immediately see which function has changed. I could then grep the open source code for that function, reconstruct the patch logic, and then reverse the vulnerability from there. If you prefer Ghidra, the kernel cache plugin lets you load XNU function signatures into the kernel cache. It auto-labels known functions using headers, which can be a huge time saver. And in the academic sense, we can even look at a case study example of this. In 2016, a researcher named OXX Reverser used diaphora to diff syslog-d from macOS 10.11.2 and 10.11.3. Only one function had changed. As you can see on the code on screen, in syslog-d's add lockdown session function, the call to realloc f plus 4 was changed to realloc f times 4 plus 4 to allocate enough space for each session and prevent a heap overflow. And for reference, a heap overflow occurs when a program writes more data to a dynamically allocated buffer than it was allocated to hold, corrupting the adjacent heap memory. It's kind of like having a row of mailboxes, aka the heap, where each box or buffer is meant to hold a fixed number of letters, or like it can only hold so many letters, right? And so if you cram, too many letters into one box, the letters might, fall out, and then they end up getting, they could potentially end up getting damaged. So if you think if like the water got on the letters or something, right? Like now you can't read them because they're all wet, right? And in this case, though, he didn't hurt the heap, so all other functions and call graphs remain identical. Inside it, he found a string that said add lockdown session realloc failed, which led him straight to the vulnerable code in Apple's open sourced syslog-d. And this kind of surgical diffing is how some vulnerabilities are reversed after a patch.
You make it sound so easy.
Oh yeah, no, it definitely takes a lot of time for sure. And this is especially important because security fixes often need to be applied across like multiple files and locations. For instance, suppose you patch identical code in files 1 and 2 on macOS, but neglect to update files 4 and 5. In that case, the unpatched files 4 and 5 still contain the known vulnerability, leaving your system at risk. It's also worth noting that updates can be platform specific. If the iOS version of file 1 is patched, but its macOS equivalent is not, macOS still remains vulnerable. Again, unless you have other mitigating controls in place. The main one is often SIP, which you can disable. The same also goes for kernel extensions. By diffing KX across versions, researchers have found changes to external method tables, surfacing newer patched entry points into IOKit drivers. As a reminder, IOKit was the thing that had like the frameworks written in C++ to manage like the hardware drivers and whatnot. And from all of this, we can see that even partial source is powerful. Combine it with binary analysis, and you can reverse Apple's systems with some surprising accuracy. And here you can kind of see that you're not flying blind, you're flying with half a map, a flashlight, and some really good tools. So, can I just build macOS? I too get ambitious with my findings, and I'm like, time to compile macOS from scratch. I have since learned that compiling these components yourself, or at least for me, is only sometimes possible and almost always painful. I'm sitting there with Apple source code downloaded and I'm ready to compile whatever it is. And after hours of frustration and dreams of achieving some new mental and or research PR, I sit with the truth, which is that you, or again, maybe just me, can't just build macOS, not completely, not cleanly, and definitely not without frustration. So what makes compilation hard? Compilation is hard due to three major reasons, I guess. First is incomplete source code. Apple regularly omits proprietary or device-specific code. For example, there's instances of all ARM specific assembly being stripped from iOS X and U, missing power management subsystems like XCPM, and to this date, some important drivers and frameworks have never and probably will never be released. Second is environment mismatches. Apple builds, like all companies, they have their own internal tools, and they build with exact Xcode versions. And if you're off even slightly with the Xcode version, you'll hit missing headers, undefined macros, compiler flag mismatches, and linker errors. And lastly is sparse documentation. And although I doubt this is new for anyone in the Apple space, if you're trying to look into this, right? You probably won't even get build instructions. Of course, there's things like community guides, right? But most of it is really just trial and error. And at least for me, I kind of end up having this feeling of very intense excitement and confusion, and sometimes even anger kind of throughout this process. You'll spend hours, resolving dependencies that Apple never documented and patching quirks that you see on screen. And also, this isn't a joke, by the way. This is a real build fix from a Mojave XNU build. So you can't fully build the OS. I even try. Well, you'll still get huge value from reading the build scripts and headers, tracing the structure and the logic, compiling parts like libdispatch, and testing patches in controlled environments, even if said patches are on a version from 10 years ago. It's still kind of helpful. So I like to think of this build process as kind of a reference model rather than a product. One tip I have is to use the iOS simulator on Xcode, which allows me to obtain working binaries with symbols and less cache extraction pain. It includes standalone dylib frameworks with public symbols, ARM64 slices, and versions very similar to real iOS devices. You can load these into IDA or Ghidra and reverse cleanly without a jailbroken device, which is really helpful if you're trying to mind your budget, right? And it's also an amazing shortcut when the source code is missing, but you still want to have visibility into system frameworks. All of this to say is that compiling Apple source code is hard and incomplete, but often worth it. Every build error teaches you more about how macOS is stitched together. And again, I try to use this process as a learning tool rather than a goal. All of that said, what did we learn? macOS and iOS both run on Darwin, Apple's open source Unix-like operating system. That means what you learn on one usually applies to the other. They share the same XNU kernel. Many system daemons and tools are cross-platform, and much of the good stuff like launchd, libc, etc. is available in source form. And again, Apple might be secretive, but its open source code is one of your best research tools. You just really have to know to use it, right? So then what's the strategy here? First, use the open source components that Apple does release, study the headers, read the build scripts, match the symbols and call patterns. Second, when things are missing, reverse the binaries. Use tools like strings, nm, class dump, bindiff, or Ghidra. Combine static and dynamic analysis, diff updates, follow breadcrumbs if you can find any. And then whether it's macOS or iOS, the internals are more open than you think. And even the gaps can be reverse engineerable with the right tools. Okay, so this talk should give you everything you need to start in this space. It's not just about compiling code or reading the docs, clearly, because the docs are non-existent, but it's about building the confidence to start exploring this massive machine. You could dig through Apple's 400 plus repos on GitHub, or just reverse a random dylib you found. And if you're curious, methodological, and honestly a little bit stubborn, I think you can do great in this space. And in terms of the content of this presentation, thank you so much for your time and happy reversing. But I have some extra notes as to where you can go from here. All citations and references are included in the slides, and yes, I will be uploading the slides. I actually never thought to upload slides until recently. And my friend told me like 2 weeks ago, she was like, oh, you should do that. But yeah, so I'll do that. It will be on my website, oliviagallucci.com. And if you want to get involved with macOS Community RL, there's 2 conferences, Objective by the Sea and Objective for the We, which I've benefited a lot from and absolutely love. That's me at Objective by the We, or for the We in Ukraine, and then the other one in Hawaii. Next one's going to be in Spain. Well, actually, no, the next one's going to be in London, then in Spain. But anyways, full disclosure, I have a lot of involvement with these conferences, and I really enjoy them a lot. There's also the Mac DevOps conference in Vancouver soon. I met the organizers last week, and they're really cool. And then if you're interested in my other work, I have some upcoming Mac internals presentations coming up the next month, and then I'm going to try to upload all of them to YouTube as well. So all of my presentations and written work are available on my website. In fact, I also recently wrote a blog post called macOS Internals for Detection Engineers. So yeah, that's like the biggest brain dump I can give you on macOS Internals. And yeah, thank you for providing me the opportunity to present.